So our first speaker this afternoon is Fengming Dong, and he's going to tell us about graphs having no chromatic zero in 1, 2.
Okay, thanks. My talk will focus on real chromatic zeros. I mean, just consider real chromatic zero. I will not go into the complex rules. Okay. Before the talk, I should show you the small place of Singapore. Okay, the university is in the western side of the island, and I guess quite a lot of you have been in Singapore or passed through Singapore. The airport is just the eastern side of the island. Okay, and the distance between the two places is about 30 kilometers only. Okay, and you see Singapore is a really very small place, just 4.7 million people about that, including overseas people working and lives in Singapore. And the whole country, the area just 620 km square. It's a quite small place.
So the moral is when we pass through the Singapore airport, we should take a day or two to visit you.
Yeah, it's quite convenient. Just half an hour can reach my university. Yeah.
But there is no sea everywhere around. This up is Malaysia. No?
Okay, there's a sea. Actually, it's an island, and the south part is Indonesia, and north part is Malaysia. Okay.
It's really island from all sides.
Yeah, it's completely the island, and there are two bridges connecting Singapore and Malaysia, and just about 400 to 500 meters long. The bridge it's quite short. Okay, and here are some photos from the campus. The campus is quite big. It's about 2 kilometers squares. It's about 0.3% of the whole country. Okay.
You may be the only university that can make that claim other than one in the Vatican.
Yes, it's possible. Okay, here are a few photos from the campus. It's quite beautiful campus. Okay, now let's go back to the talk. Start from 1912. Okay, because the chromatic polynomial was first introduced by Burkle in 1912. Okay, I don't need to say anymore because it's very clear to everybody already. And just some references, I think these may be necessary for some of you because you may be interested to know more about chromatic polynomial and detail the properties of chromatic polynomials. And there are a lot of papers on chromatic polynomial. Here I just choose a few articles only. The first one is it's by R.C. Reed. I think he's once worked in Waterloo. Okay. The paper is Introduction to Chromatic Polynomial. For me, I read this article. This is the first article on chromatic polynomial I read. Okay, and the second one is by Reed and Ta. Okay, it's in the book Selected Topics in Graph Daily Tree. Okay, it's another article. Okay, and both articles are very helpful for you to know more about the property of chromatic polynomial. Okay, there is also one book published in 2005 and by World Scientific in Singapore. Okay, and this is the book you can find from website also. Okay, it's just focused on chromatic polynomials, and we also study the chromaticity of graphs. What chromatic means, we study a family of graphs which have the same chromatic polynomial. Okay. Okay, what is polynomial? It's very easy. There's another expression to say the chromatic polynomial is really a chromatic polynomial. It's really a polynomial. Okay, this is another expression here. For every graph, order n, we can always find the number of partitions. Okay, there's the number of partitions of the whole vertex set into k non-empty independent sets. Okay, so this alpha gk represents this number. And then we have a polynomial expression for the chromatic polynomial. Okay, and the second one is, you can see, is just the special case. Chromatic polynomial is the special case for postmodel when every h the weight is -1. Okay, so there's a very nice expression here. Okay, now I want to define chromatic zero. Chromatic zero means just the zero, the rule of the chromatic polynomial of the graph. Okay. Okay, now I need to define a family of graph. Okay. Later we will use this family F. We always use F to represent the family of graph which have no zeros between 1 and 2, real zero between 1 and 2. Okay, so we use F to represent the family of graph. And this family including those, every graph, all graph maybe disconnect, maybe just connect, but they are not bros. Okay. And we apply one result, Jackson's result in 1993. Every graph has no chromatic zeros in this interval between 1 and 32/27. So when we study the question, what graph are in F, we don't need to consider the interval in this interval. We just need to consider the other part, okay, 32/27 to 2. Okay, that's very clear. So we just need to consider this interval, that's all. Okay, now there are two problems. First problem, give any graph. How can I know the graph is in F or not in F? Okay, I think this may not be easy to judge the graph is in F or not in F. And the second question, second problem here, can graphs in F be categorized by their structures? It means if you tell me a graph where I'm able to tell you just from the structure, I don't need to do anything about the chromatic polynomial, just from the structure of the graph. See whether we can find structural property to decide, to say the graph is in F or not in F. Now, for example, there are some property, for example, the bipartite graph, okay, connected bipartite graph. If the number of order is odd number, then the graph, I'm very sure this graph is not in F. Now, for example, this graph. Okay, this one is a bipartite graph. Okay, this is a bipartite graph, and odd number of vertices connected. So I'm very sure this graph is not in F. This is 0. Okay, this is 0 between 1 and 2. So for this one, I'm able to. So for some graph, I'm able to tell the graph is in F or not in F just from the structure. And there are two famous conjectures about this problem. One conjecture is by Jackson, 1993. The condition is if graph G is tree connected and non-bipartite, then G belongs to F. First time when I show this conjecture, I really don't understand why we need these two conditions. Because since there are no much relation between them, the two conditions, tree connected and non-bipartite. Okay. And then it's not difficult to find. You study those graphs without not three connected, maybe two connected graphs. We cannot guarantee two connected graph is in F or not in F because there are some two connected graphs which are not in F. So probably from here we can understand why we need three connected, and also non-bipartite easy to understand. Bipartite graphs some are not in F. Okay, so we need these two conditions, but it seems not easy to use these two conditions to study the problem.
How would you possibly use the condition that a graph is not bipartite?
Asking me.
I don't know.
Well, you could use deletion contraction on an edge which doesn't belong to an odd cycle, or distinct from an odd cycle.
Okay, and the next conjecture is Thomas' conjecture in 1993, and the condition is the graph must be Hamiltonian. Okay, so the graph Hamiltonian and the graph belong to F. Okay, now I have to talk about the motivation why I study this kind of problem. Okay, first you see all these problems themselves, they are very interesting. Okay, if you don't need to consider linking between these problems to others, themselves, they are really very interesting. It's worth to study. And the second one, the motivation for me is there are two very famous conjectures about the flow polynomial and the chromatic polynomial of planar graph. And these two conjectures, I have been trying very hard to do these two conjectures for a very long time, but I cannot find any tool, any useful method to do them. So I'm trying to find some method to do the two conjectures. So that's another motivation to study the problems on the chromatic zeros between 1 and 2, those graphs without chromatic zero between 1 and 2. Okay, that's my motivation. Okay, now I need to start to say about something about the chromatic zero. Why we have to find the family F. To determine the family F, actually we just need to consider two connected graphs. Okay, why? First, you see, if the graph G is not connected, it means there are a lot of components. And from this property, we find all the zeros of G actually is the union of zeros in all these components, chromatic polynomial. Okay, so it means to find the zeros of G, we just need to find the chromatic polynomial, the zeros of these graphs per chromatic polynomial, G1, G2 up to Gk, all the components. Okay, that is the first result. Second one, if G1, G2, Gk are the blocks of a connected graph G, now suppose G is connected, then it seems, because we have this expression, so it seems the chromatic zero of G is the union of all chromatic zeros of all these blocks. Okay? So by this result, we can find, we just need to focus on non-separable graph. We don't need to go into the disconnect graph or just one connect, not two connect graph. So now we have this result. Now we can say the graph G belongs to F if and only if all blocks of all components of G belong to F. Okay? So to determine F, we just need to determine all the non-separable graphs in F. Or you say just consider two connected graphs in F because the only difference is K2. Okay. Okay, now I want to show you some examples. Okay, non-separable graph in F of small order. Okay, the first result is all graphs of order and most 5 belong to F except the one graph only. Okay, so you just need to consider there's only one graph not in F, K2, 3, if the order is S and most 5. Okay, so we have K2, we have K3 in F. Okay, I need this graph. Okay, now consider all of 4, there are 3. One is the cycle, okay, C4. And complete graph K4, okay, and complete graph remove one edge. And the tree graph, let's see, they are very important here. I want to show the idea later, how I study. Okay, this one belong to F, this one belong to F. And why C4 belong to F? If I don't find the chromatic polynomial, can I judge whether this graph belong to F or not? I mean, I don't do anything about the chromatic polynomial. I say I can do it because this is a cut set. Okay, take these 2 points, a cut set. And you remove these 2 points, you produce 2 components. Okay, and both components we will find, contract them and add the edge to here. We find small graph. For example, I add edge to here. Again, this component belong to this graph here. And this component also, okay, this part also is a graph here. If I contract them, if I identify these two vertices, I get a graph. It's this type graph. Okay, so these two parts both are here. Okay, that's the result later I will show you. Okay, and for this graph, you can see there's a complete cut set here. Okay, and for the complete graph K4, this is 3 connected graph. So I can take any edge remove this edge or contract this edge, and the graph I produce belong to this one, yeah, or belong to this one. Okay, so that's the small graph. And for
So you're saying there are general principles for generating new graphs in F from O?
yes, later I will show
Two
you.
graphs in F and glue them together at
Yes.
a 2-vertex cut that stays in F?
Yeah, and yes, that's enough. Later I will show you.
Okay.
I will try to find graph in F recursively from small graph to big graph. That's the idea. Okay, but these are special examples. Okay, now let's see the counter example K23. Okay, K23 is not in F. And the chromatic polynomial we can find, and this real zero is about 1.4 something, okay? And K23 is quite important graph here. Later I show you some result about K23, okay, again. Okay, now let's see some well-known result. Some graph belong to F. First one is color graph. And it is very trivial because color graph only have chromatic zeros, integer, non-negative integer chromatic zeros. So it's not possible you find zero between 1 and 2. And another result is Burkov and Lewis result in 1946 on planar triangulations. And Woodard has another result is up planar graphs. Okay, and these are well-known results about graphs in F. Okay, now I'm going to show you how I do, how I try to find a family. I first had to find a fundamental result. Okay, I first had to establish a fundamental result. Okay, that's the first step. And the second step is try to apply this fundamental result to prove a family of graphs. A family graph, a whole family is a subset of F. I don't want to focus on one graph. Okay, I don't want to focus on one graph. I take a family. Okay, and for example, Thomason's conjecture, people can take the family of Hamiltonian graph and include one more, K2. So to study your problem, we need to take one more as K2. K2 and the set of all Hamiltonian graphs. Okay. So I first need to introduce S-bridge, although Jackson has introduced this concept last week. Okay, I repeat again. Suppose G is a kinetic graph and S is a subset of vertices. And if V1, V2, Vk are the vertex set of the components, and then we define S-bridge, the subgraph of G induced by this set, the union S and Vi is called S-bridge. So if G minus S has K component, then the graph has K S-bridges. And here is one example. Okay, let me show you. Okay, we take this graph and take this S. Okay, now it's very clear this graph has exactly 3 bridges, S-bridges. I mean S-bridge. S is defined to be the set of the 2 vertices here. Okay, and this is one bridge, one S-bridge. And this is another S-bridge. And here's the last one, the third S-bridge. So it's very clear that S-bridge means you have to include the S and also the component of the removed S. Okay, now we have first result. A 2 kinetic graph G belong to F if one of the following conditions holds. There are 4 conditions. As long as one of the 4 is true, then G is an F. Okay, the first one. G has an H UV such that both G minus UV and remove the H UV, and G contract UV are non-separable graphs in F. Okay, I want to show you the proof, very short proof. Okay. Now first I need to define a function, another function. Okay. Okay, I need to define another function. It's not the chromatic polynomial, just slightly different. Suppose G is non-separable, okay? G is 2 connected or K2. Then I define the function Q, and I just add in one sign here, -1 to power n. N is the order, okay? N is the order. And there is one famous result, in Jackson's paper. You can see G belongs to F if and only if QGX is always positive, okay, for all S between 1 and 2. Now here the condition is G must be 2 connected, or K2. Okay, so if G is an F if and only if the function QGX is always positive for all S between 1 and 2. Okay.
Because -1 to the n is the sign that the chromatic polynomial will have at 1 plus epsilon. And in fact, up to 32/27.
Yeah, it's based on his result. It's just the small interval between 1 and 32/27. That period, this function is always positive. So if there is 1 point negative, then there must be 1, 0 between 1 and 2. Okay. So I need to use this result. Okay, now G is a graph, and UV is 1H, okay? So now chromatic polynomial of G is equal to PG minus UV minus the chromatic polynomial after you contract UV, okay? Contract UV. So there is this relation. And then it's not difficult to prove QG HA is equal to QG minus UV and plus QG contract UV. Why here the change of the sign from negative to minus to plus is very easy to understand, because when we define a function here, there's one sign is -1 to power n. N is the number of order. And this graph, G contract UV, is just one less than the order of G. So just easier to change the sign from negative to plus. Okay? And now both G minus UV and G contract UV belong to F. So both function values are positive. So the sum is also positive. That's why if both G minus UV and G contract UV are the graph, non-separable graph in F, then G must be in F. Okay? And the second condition says if G has a complete cut set S such that all S bridges belong to F. And this is easy to understand.
What does complete cut set mean?
I mean, the cut set form a complete subgraph.
Ah, okay.
Induce a complete subgraph. Okay. Now take example. For example, is K3. Okay. And this is a subgraph here, and this is a subgraph here, or even more. Never mind. Okay. No matter how many, and we have a formula to express the chromatic polynomial of the whole graph in terms of all the subgraphs. Okay. And the result says PG lambda H is equal to the chromatic polynomial okay. Suppose the subgraph induced cable research and the number of components, so here is probably use M. Okay, here's M minus 1. If there are M minus 1 subgraph here. Okay, 1, 2, up to M. So, and this is the complete cut set. Okay, and there's a formula here. And from this formula, you can see if G has a chromatic 0 between 1 and 2, then some subgraph GI must have chromatic 0 between 1 and 2. Okay, so as long as all S bridges belong to F, then G must be in F also.
Excuse me?
So I don't think I understood the definition of an S-bridge. So when you take an S-bridge, you take all the vertices of a component of the complement
Yes.
and all the connecting edges.
Yeah, just the induced subgraph here is the means we consider induced subgraph of this set. Is the subgraph G induced
Okay.
by the union S and VI?
So it's one of the pieces that you would glue along S to reconstruct the whole.
Yeah, including S. Okay. And induced subgraph means we have take all possible edges in this subgraph. Okay. And for example here, okay, if S is this one, then there are 3 S components here. Okay, this is the first one. We take these 2 vertices in S and also take 3 vertices in this component here. Okay? And this is the induced subgraph. We have to take all possible edges in the original graph here. Is that clear?
Yes, thank you.
Okay, then part 3. Part 3 say, okay, now we go in some part, it's quite complicated. Okay, 2 vertices, it cuts set X and Y. X, Y are not adjacent. Okay, S, Y not adjacent such that CG minus S is even. The number of components must be even. And all S bridges G plus XY, and all blocks S contract X, G contract XY belong to F. Let me show you one example. Okay, now suppose I don't know this graph, a very simple example C4. Okay, and I have SY here. But I know K2 and K3. I know these 2 graphs both belong to F. Okay, I just have this information. Both K2 and K3 belong to F. Okay, now I want to judge this graph. So take 2, let's consider these 2 subgraphs. These 2 graphs. First is add in one edge between S and Y. And second one, identify the 2 vertices. Okay, so I get 2 graphs. One is, you can say this one is G plus SY. Another one is G contra XY. Okay? And this S bridge, okay, S is the set of vertices S and Y. So there are 2 S bridges. This is one and this another one. And both are this graph K3. Okay, K3 is an F. And for another one, after I contract, I identify these 2 vertices, I get a graph. It's not 2 connected graph. So there are some blocks here. Now here, there are just 2 blocks, and both are this graph belong to F. Okay, so here the condition is such that CG minus S is even. The number of components after you remove S is even. And all S bridges of G plus SY and all blocks of G contra SY belong to F. There are the 2 conditions. Okay, under these conditions, what I can do is to prove QG lambda. I can prove under this condition will be equal to Q G plus XY and plus another function G contract SY. But here must be careful, QG contract SY is not 2 connected, and there is an extension of definition for this those graph separable if G is not 2 connected, and if the definition is here B is the number of blocks. Okay, B is the number of blocks. It's also positive. So if both belong to this family, we can prove this is positive and this positive, and the sum is positive. That's the idea to prove for this result. Okay, and just last week after I come here, I'm trying to find some condition for another case. If the number component G minus S is not even, it's odd, what happened? And I find it's very nice, the result can be changed, can be extended to here. If G has a cut set, SY also disconnect. And we need three conditions. Okay, G minus S has odd number component. That's first condition. Second one, all S bridges of G plus SY and all bros of G contract XY belong to F. It's same. But we need one more. We need one more. Every S bridge of GI of G. Don't do anything. Don't add H, don't contract. Just take every S bridge of GI. And the number of components must be odd. And all blocks must be in F. Okay, now here I need to show you example. Okay.
Sorry, Frank, man. Goes now.
Hmm?
So, is an S bridge not necessarily connected?
No, on the example he gave, remember the third of his S bridges had one of the two vertices isolated.
The S bridge must be connected.
No, the S bridge of G plus XY will be connected, but the S bridge of G might not be connected.
And this one.
Yeah.
This one also
this example he gave had a disconnected S bridge. Do you remember?
This is connected, but may not be too connected. It's connected.
So I'm asking about C of GI is odd. Is C of GI not 1?
C,
The third condition.
this one, the first one.
No, the third condition.
This one.
Yeah?
If CGI is not, I don't know anything. It may not be in F. Okay, so I need this condition. CGI must be odd.
Bill, remember the example he gave? If you go back to the example you gave of a decomposition with 3 S bridges, the rightmost one of his 3 S bridges was disconnected.
But here it's different because this graph is not two connected. If under the condition two connected, then every bridge should be connected, but I cannot guarantee it's two connected.
But then, if that's the case, then Bill is asking why do you need this third condition that C of GI is
Yes,
odd?
because and here the proof is not easy, but I use the example to show you.
No, but he was saying, why do you need a condition that C of GI is odd if you know that C of GI is 1?
GI is 1 also is all fine. The number component is 1 is all fine. If it's 3 connected, or if, for example, maybe three blocks. Okay, I show you example. Okay. Okay. There's a maple file here. Okay. Now let's see. This is the complete bipartite graph K2 tree. Okay, I use Maple to run through the process. You can see this bipartite graph. Okay, has a 0 between 1 and 2. It's about 1.4 something, right? Okay, and you see this complete bipartite graph. So x, y, so there are 3 components here. Okay, there are 3 S bridges. If you take x to be the union x and y, so there are 3 S bridges. 1, okay, 2, and 3. There are 3 S bridges here. Okay. But now I construct another graph is also 3 S bridges. However, I change this part S bridge change into just slightly different. I mean, every S bridge has 3 components. Now here, every S bridge has 2 components only. Now here, every S bridge has 3 components.
3 blocks.
3 blocks. 3 blocks here. So I consider this graph. Okay. And here it's between vertex 1 and vertex 4. So there are 3 paths connecting 1 and 4. And every path has 3 edges. Okay? So you take 1 and 4 from the set S. Okay? So we have 3 S bridges. Every S bridge has 3 blocks. Okay, now let's see what happened. The chromatic polynomial, this graph has no 0 between 1 and 2.
Can you go to the statement of your theorem?
I think maybe where he wrote C of GI, maybe what you meant was B of GI.
Here is use the number of blocks is to adjust the sign of Q. Make sure the summation, okay, it's not to adjust the sign of the Q. I just make sure to compare or the 2 pi is first term is bigger than the second term.
Yeah, I think we understand. I think there's just a typo on your slide. I think your C should be a B.
Okay, let me see. Oh yeah, sorry. Here it should be B. You're right. Yeah, yeah. Yeah, you are right. Right.
Can't do that in PDF.
Not easily.
Okay, right. So here it should be BGI. Yes, right. Lot number component. Okay. So now we use datum 1, datum A. We can get another datum is datum B. Okay, I don't want to prove datum B. Datum B is completely based on datum A, but it's quite useful. You see, now I take any set of family U, and this family U, I want to include K2 and K3. Okay, I don't need to include K1. K1 is not necessary to consider. Okay, I just need to take K2 and K3 and some 2 connected graph. Okay, now I form this result. And then the whole family is a subset of F if one of the following conditions holds for every graph G, or order at least 4. Okay, and the first one is G must have one edge UV such that G minus UV and G contract UV both belong to the family U. Why are you need to use this condition? Because are you doing by induction? Now suppose smaller graph already belong to F. Okay, I mean these two once they belong to U, it means they also belong to F. And the second one also similar. If G has a complete cut set such that all S bridges belong to U. And the third one I just consider the case the cut set as Y from the set such that the number of components is even, and all S bridge of G plus SY and all blocks of G contracts Y belong to U. Okay, so actually here I did include part 4. I can include part 4 also. Okay, now let's go back to Thomason's conjecture. I have tried to prove his conjecture by doing such a way. Take U to be the family of K2 and Hamiltonian graphs. Okay, just add the graph K2 into the family. Okay, and then Thomason's conjecture is true if this conjecture is true. It's another conjecture. Okay, if every 3 connected Hamiltonian graph contains an edge UV such that both G minus UV and G contract UV are Hamiltonian graph, and we go back belong to the family also. Okay, why we just need to prove this part. The reason is very simple. If the graph is not 3 connected, then the graph has a 2 vertices cut set. 2 vertices cut set, there are 2 cases. Either 2 vertices adjacent or not adjacent. And both can be split into smaller graph with Hamiltonian cycles. Okay, that's the idea. And there's a result about Hamiltonian cycles. Beard's result in 2006. I don't know if it's 2006 or 2007. Maybe here I made a mistake, maybe in 2007. Here they say if a graph G has minimum degree 3 and G has a Hamiltonian cycle containing at most one edge of every cross in G. And then the graph has one edge E such that G minus E and G contract E both are Hamiltonian. Okay, that's the partial answer to Thomason's conjecture. So if we just consider crop free, Hamiltonian crop free, then of course the graph has one edge such that both G minus E and G contract are Hamiltonian. Okay, now I'm going to introduce one of my recent results to produce one family, and this family is a subset of F. Okay, how do I do it? First, I need to find an ordering S1, S2 up to Sn. Now, suppose these are ordered vertices. It means n vertices, I take one order, S1, S2, S3 up to Sn. And define Vi. Okay, what's Vi? Vi is the intersection of the neighbor set Si and those vertices before Si. What I say before Si, I just consider those neighbors S1, S2 up to Si minus 1. For example, consider V3. V3 just consider V3 is just equal to neighbor X3 in the intersection X1, X2. Just consider these two vertices.
Should we also include xi?
No.
No.
No. And because the graph is simple graph, it doesn't have a loop come back to the point. Okay, and now I define a special type of order called gamma order. So if the order satisfies this condition, the first two vertices S1, S2 must be adjacent, and for every non-empty I, either satisfy this, either some Vi for some I and I is not independent set, or the union of all these sets is the cardinality is just one bigger, it is one bigger than the size of I, the selection of number of integers in this set 3 to n. So this condition is very similar to Hall's theorem. It's just one bigger. I mean the union is just one bigger. Okay, so either the first one, some Vi is not independent. Okay, here I need to show you one example. Otherwise, it's not easy to understand the condition here. Okay, let me show you one graph. Now, for example, this is bipartite graph. Okay, take this complete bipartite graph. Okay, it's a complete bipartite graph. Okay. And I need to add in one more edge. Okay, now I start to label. Okay, label this as 0, S1, S2. Okay, for example, this S3, S4, S5, S6, S7. Okay, probably I add 1, 2 more because in two favor is just 1 point here. Okay, S8, S9, S10. And this is the label of vertices here. Okay, let's see now the sequence S1, S2 up to S10 here. So V3 is the set of vertices here. V3 the order, V3 V3 has two vertices only, S1, S2. And this is not independent set. So I don't need to consider V3 because 1 and 2 are adjacent. And X4, so you consider V4. V4 also not independent. V4 not independent. And V5, same, not independent. V5, V6, V7, all these sets are not independent here because every set contains the two vertices S1, S2. And these two are adjacent. Okay, now I consider the others, XA. SA, so VA are the vertices S3 up to S7. And it's the same, V9 and V10, all the three sets are same. Have these vertices, S3, S4, S5, X6, and X7. Okay, so all the possible troubles are these sets, VA, V9, and V10, because now you see the first condition. As long as some VI is not independent set, it's fine. So when we choose the set I, if once which means some VI is not independent, we don't need to consider. So we just consider case if we choose the I and every VI is independent set, then we have to consider the second condition. Okay, so now you see VA, V9, V10, the three set, every set is equal to the set vertices S3, S4, S5, S6, S7. So of course you will see the second condition is true because the cardinality of every set VA, V9, V10 is equal to how much? 5. Okay, so this is really a gamma ordering.
So another way of saying it is, let's define J to be the set of vertices for which VI is independent. And then we just consider I's in J and look only at condition B.
Yeah.
That would be the same thing, right?
Yeah. If they are not independent, we don't need to consider.
Right.
Yeah. Okay, so now easy to find there's a result here. If S1, S2 out to Sn is a gamma ordering, then S1, S2 out to Sn minus 1 is also a gamma ordering. It's also a gamma ordering. So now we suppose this is the family of graph which has a gamma ordering, okay? And there's some properties here. First one, every graph in gamma, as long as the graph is not K2. K2 is also a graph in gamma. If the graph is not K2, then the graph must be 2 connected. It's not difficult to prove it. Okay, and also the graph should have triangles, it means K3. Okay, and the graph always has a vertex X such that G minus X belong to gamma. Okay, and also you add any edge SY, you always get a graph also in gamma. I mean G plus XY also in gamma for any G in gamma. So you add any edge, then the new graph G plus S also in gamma. But this property in general is not true. We cannot say if a graph is in F, then plus A in one edge also in F. I'll show you one example. Okay, this is K24. Okay, K24 is in F. K24 has no zero between 1 and 2. But if I A in one edge, now it's different. If A in one edge, we have trouble. So in general, this property is not true. However, in the family, gamma is correct. Okay, now the minimal graph in gamma. Okay, because we have the property if a graph in gamma, then we A in one edge, the new graph also in gamma. So we can consider minimal graph in gamma. Okay, so what are the graph in gamma? First one, the smallest one is K2, then K3. And for order 4, the smallest graph in gamma is K4 minus E, it means remove one edge. Okay? And for order 5, there are 3 minimal graphs. Okay. There are 3 minimal graphs here. So means from this minimal graph, n edges, anywhere n edge always produce graph in gamma also. Okay. So from this, probably now we find the graph in gamma can be produced recursively by a and new edges, new vertices and new edges. So for every graph G, we can always produce the graph G from a smaller graph in H, a smaller graph H in gamma, and by adding a new vertex and some new vertices. Okay. So there's one result. I say the whole family gamma is in F. It means every graph in gamma has no chromatic zero between 1 and 2. So that's the family we've discovered. So every graph has no chromatic zero in between 1 and 2. Okay, now there are some interesting results here. The first one, you see, Thomas and Prue, if a graph has a Hamiltonian path, then we can guarantee there are no chromatic zero between 1 and 1.2 something. And this number can be found from a function from an equation. However, may have zero between this period, this interval, okay, between this number and 2. But now we add one more condition, okay? Just add one more condition. Suppose S1, S2 up to Sn is a path, Hamiltonian path, okay? And also they satisfy this condition. Every vertex has two neighbors before it. For example, S3 has two neighbors, S1, S2. And S4 has at least two neighbors among S1, S2, S3. Okay? So under this condition, we can guarantee the graph, this graph has no zero between 1 and 2 because it belongs to gamma. And the second one says if there's an ordinate S1, S2 up to Sn, and such that every set, this kind of set NSI, intersect the vertices before Si is always not independent. Of course, the graph is in gamma. Okay, and the special case are those graphs. If the graph contains a 2-tree as a spanning graph, if a graph contains a 2-tree spanning subgraph, then the graph must be in gamma. And also two connected planes near triangulation. And also complete T-partite graph. T is at least 3. All these type graphs, okay, they are special examples. And corollary about the connectivity. Okay, every graph, as long as n minus sigma plus n minus delta plus 1 connected graph, everyone is in gamma. Now here, the delta is the measurement degree. N is the number order. Okay? And the result is the best. We cannot replace when delta is less than n minus 2 or equal to n minus 2. The result, the n minus delta plus 1 cannot be replaced by n minus delta. Okay, the example is K23. K23 is two connected graph. Okay, it's two connected graph, but K23 has 0 between 1 and 2. And another one is bipartite graph. And bipartite graph, we know the complete bipartite graph, we cannot guarantee complete bipartite graph has whether it has 0 between 1 and 2 or not. However, we just need to make a small change in one edge somewhere and can make sure the new graph has no 0 between 1 and 2. Okay? And now go to our top. And our top, Gordon has already introduced the concept of our top. And every graph in gamma is also our top. That's the result, okay? So I go faster. All graph in gamma are our top. So there's another conjecture about the graph in F. So every our top graph contains no 0 between 1 and 2. And this condition, our top, this condition is weakened in Thomason's conjecture condition, Hamiltonian cycle. So they have this relation, the family of graph our top and the family of Hamiltonian cycle and the family of gamma graph. And that's the we guess the the family of our tau graph should be in F. Okay. I say I don't have much time. I show you just one slide, one interesting result about the minor closed class. That's the last one. Okay. I don't want to say anymore. Suppose omega is a set of graph, and we say omega is minor closed, means if all the minors of G is also in omega. Okay, it's not as all the minors are here. And it's a very interesting result. If omega is minor closed, if omega is minor closed, and the whole family is in F if and only if K23 is not there. So we just need to see whether K23 is in the minor closed family or not. If K23 is in the family, then may not be true, because K23 itself is a graph has 0 between 1 and 2. Okay, if K23 is not in the family, then the whole family, 4 minus closed family, is a subset of F. And this result is coming from here. Just from here, from the next theorem, K23 is not a minor of G. If K23 is not minor of G, it implies G is in F. So if K23 is not minor of G, but in the other way, if the other direction, if G has a minor K23, we are not sure whether G is in F or not. Okay, but if we find K23 is not minor of G, then G should be in F. Okay, so datum D just come from datum E. The proof is very easy.
Is that because you have a characterization of graphs with no K23 minor that are somehow built out of outer planar ones plus K4s?
They're very highly two-separable, right?
It's very easy to prove. Just use the beginning of the result, datum A or datum B to prove it. It's very easy. Just take the family of graph G, take the family G and all the minors G also. Just take this family and use the datum B to prove it, the second result to prove it. It's quite easy. Okay. And the last one is the graph. I'm going to show you is the multiplicity of root 2 is equal to, okay, this graph is also in F. However, this graph is very special, has one more property. If we chose suitable K, this graph has 202. Okay, and why this is interesting, because we know some results about okay, here, for kinetic graph, we know the multiplicity of root 0 of this chromatic polynomial is always 1 if G is kinetic. If G is 2 kinetic, the multiplicity of root 1 is always 1 also. So then it's very natural to ask the question, if G is 3 kinetic, whether the multiplicity of root 2 is 1 or not. Okay. So the graph is just a counted example to answer this question. Means there must be some 3 kinetic graph, the multiplicity of root 2 can be bigger than 1. Okay, that's all.
Does your last graph belong to gamma?
I don't think so. Let me see.
I guess what I meant is, could it be true that if J belongs to gamma, then
No, I don't think so. It's not easy. No, I cannot judge this is equal in gamma. I cannot say it's in gamma.
so could it be true that if J is in gamma and J is 3 connected,
If K
then
is
J
smaller,
is
it's
a-
possible. If
Then-
k is smaller, it's possible. If k is quite big, maybe not. No, it's not, because this is not alpha tau when k is very big.
So could it be true that all three connected graphs in gamma have a symbol 0 at 2?
I don't know. This is another question. I don't know.